Hello friends, welcome to Physics Bro YouTube channel. We are starting thermodynamics. Plus statistical mechanics. This is exclusively for IIT JAM physics. Okay, so there are 7 units for IIT JAM physics. Thermodynamics is one of them. You can see the 7 units and their mark distributions in next slide here. So we are starting this unit, I mean kinetic theory. It includes 13 marks in general, 13 marks for this unit, I mean thermo plus static. This is general, not sure. Every year it will not be 13. In some years it will be 10, and in some year it will be 10. There will be 2 mark or 3 mark up and down. In general, we can say 13 mark will come from this unit. So also the questions from this unit will be easy or moderate questions will ask. So it is easy to attempt the question, and it will help you to score good mark and good rank in your exam. So let's see what are the chapters in this unit. So mainly there is 9 chapters. 9 chapters are there. We will take all these 9 chapters in this particular order. So first we will begin with kinetic theory of gases. This chapter, kinetic theory of gases. So usually kinetic theory of gases, maybe in short we can write it is as KTG. Specifically from this chapter there will be 2 questions. From this particular chapter, kinetic theory of gases. This also keep in mind, it is also an average value, 2 question. Maybe it will be 3 question, maybe it will be 1 question. It all depend on particular year, but in general there will be 2 questions from this chapter. So this chapter is a very important chapter. So let's begin our chapter with the first topic in that. So the first topic in this chapter is, of course, postulates of kinetic theory. So the very first topic is postulates of kinetic theory of gases. Postulates simply means assumptions. We are going to assume the behavior of gas molecules. Okay, so before going to the postulates, it will be clear that we are aiming for our approach is for a competitive exam. So we will not go all the theory part. We will look at the importance theory, and we will move to the problem sections. So keep that in mind. Okay, so the first point. Let's start the postulates. So for that we will consider a container. In this container there are many number of gas molecules. These dots represents gas molecules. Okay, let's say there are n number of gas molecules, and the volume of this container is V. Okay, so the first point by comparing the size of, the volume of this container, these gas molecules are very small, so we will consider that as a point particle. Okay, so the gas molecules behave as a point particle. Okay, then the second point is these gas molecules are in constant motion. They are moving, but not in a straight line fashion. They move in random direction, like if they move like this and like this, like in random directions they will move. Okay, so that is the second point. Gas molecules moves in constant motion. Their velocities are constant in random direction. Okay, so the third point is, as you can see, when these gas molecules move, there is a chance of colliding these gas molecules with another gas molecule as well as with the container. So gas molecules collide with each other and with boundary of container. Okay, so these collisions are conservative in nature. Also keep that in mind. Conserve. There is no loss of energy during this collision. And the fourth point is, there is no attraction between these two gas molecules. No attraction or interaction. Let's say interaction. No interaction. That means they are very far apart from each other. That's why there is no interaction. And the fifth point is, these gas molecules will obey Newton's laws of motion. Newton's laws. Okay, so these are the 5 points that mainly say the postulates of kinetic theory. So let's move to next topic. So the next topic in this chapter is pressure excited by gas. So actually this is a very important topic. Okay, so we already consider the container like this, and there is a large number of gas molecules, because we also seen that these gas molecules will collide with each other and also will collide with the walls of the container. So this collision will lead to the pressure. So the origin of the pressure is this collision. So origin is this collision. This collision is the origin of this pressure. We know that basically a pressure is, we can define pressure as normal force by area. For example, if you take a surface like this, if you consider a surface like this, let's suppose there is a force acting like this, F, with a theta angle. Then this force, we can resolve this force as two components, which are one in this direction and another in this direction. Here this component will be F sin theta and this component will be F cos theta. Then here the pressure in this case, in this particular case, this let's suppose this area is A, then pressure will be F cos theta divided by A. this is the basic definition of pressure. So let's move. So in our case, the formula I'm going to write the formula directly. I'm not going to the derivation part, because we are aiming IIT JAM entrance, so no need of derivation. So this is the formula: P equal to 1 by 3 N by V M V square average. So this is the formula of the pressure excited. This is very important formula. Here N is the number of gas molecules and V is the volume and M is the mass, and this V is the velocity. Here V square average is we can write V1 square plus V2 square plus V2 square plus V3 square plus etc plus Vn square divided by N. This is V square average, means V1 is the velocity of first molecule and V2 is the velocity of second molecule and Vn is the velocity of nth molecule. We will sum it over N. So this is the formula. We can rewrite this formula by using mass density. Let's look at how will come. Okay, so move to next page. We saw that the formula is we know P equal to 1 by 3 N by V. N is the number of molecules, N by V, M V square average. So we can rewrite this equation by using mass density. So mass density usually denoted by rho. Rho is N into M, that is total mass divided by volume. This is the rho, so we can substitute this here. This term here, this term will become rho. So our formula become P equal to 1 by 3 rho V square average. So this is also a formula for pressure excited by the gas. So here you can see there are two formula. First one is this, P equal to 1 by 3 N by V M V square average, and the second one is pressure P equal to 1 by 3 rho V square average. So these are two important formula. You must by heart these two formula. So let's move to the question. One question based on this. In question it says that 100 mole of gas contained in a cube of 0.8 meter cube. Okay, then mass of gas molecule is given. Molecule is 5 into 10 power minus 23 gram, and the translational speed is given. Translational speed also given, which is 483 meter per second. So the question is, what is pressure? What is pressure exerted by gas? So this is a question for this is first question. Let's move. This is actually a direct question, very direct question. So our formula is P equal to 1 by 3 N by V M V square average. Okay, this is our formula. So here N is 100 mole. 100 mole is given. 1 mole, we know 1 mole is equal to what? Avogadro number of molecules, means Na. 1 mole is equal to Na, means 6.02 into 10 power 23. So N is here, N is 100 into 6.02 into 10 power 23. This is N. And V, volume, is 0.8, which is in meter cube. And M is 5 into 10 power minus 23 gram. So we need to convert this into kilogram. 5 into 10 power minus 23. This is in grams, so we need to convert to kilogram by multiplying 10 power minus 3. And velocity, which is given in SI unit, that is 483 meter per second. So this is very direct question. Put these all values into this formula. So then we get 2.95 by 2.95 into 10 power 5 Pascal. Pascal is the SI unit. So we forgot to talk about what units of the pressure. So let's talk about that a little. So unit of pressure, units pressure. First point in this, that SI unit is Pascal. Pascal. In commonly we use ATM, atmospheric pressure, and 1 ATM is equal to 1.01 into 10 power 5 Pascal. Okay, 1 ATM is equal to 1.01 into 10 power 5 Pascal. There is one more units we saw, bar. 1 bar is nearly equal to 1 ATM. So these are about pressure, units of pressure. So before ending this lecture, there is a relation between pressure and the translational kinetic energy. Let's look at that also. We know pressure is what? 1 by 3 N by V mv square average, right? And also we know that E, energy E, is half mv square. This is for one molecule. For n molecule it is like this. So by using these two, we can write pressure is equal to we can substitute from this, we get what? mv square n. This quantity become equal to E, right? So put here 2E. Okay, so we get pressure is equal to 1 by 3 into 2E by V. That is, pressure is equal to 2 by 3 E by V. E by V. E is the energy and V is the volume. So this is an important relation between pressure and energy. Relation between pressure and energy. P equal to 2 by 3 E by V, or PV equal to 2 by 3 E. PV equal to 2 by 3 E. Also we can rewrite this equation in some another fashion also by using ideal gas equation. Let's see that also. Now we got PV equal to what? Wait 1 minute. Okay, so we got what? PV equal to 2 by 3 E, right? This is one equation. We know that in case of ideal gas, we know that PV is equal to what? nRT. PV equal to what? nRT. So let put PV by use these two, 1 and 2. We can write 2 by 3 E is equal to what? nRT. From this we get expression for energy, that is 3 by 2 nRT. So this is the expression for energy, that is translational kinetic energy. So we got equation for translational kinetic energy. Let's rewrite that in a new slide. We got translational kinetic energy formula, that is E equal to 3 by 2 nRT, right? We can rewrite this equation further by using Boltzmann constant, because KB, Boltzmann constant KB is equal to R by Na, right? We can write E is equal to 3 by 2 N into, instead of R we can write KB into Na T. Okay, the number of moles, right? Number of moles. So number of moles into Avogadro number gives number of gas molecules, that is our capital N. So here N into small n into Na we can replace by capital N, so then it becomes 3 by 2 NKBT. So we got another formula which is in KB, that is energy, translational kinetic energy, that is E equal to 3 by 2 NKBT. So these are the some formulas which will help in problem solving. Now till this we saw many formulas. Let's revisit that before ending our lecture. So at the end of this lecture, let us look at the summary. First we look at the postulates of kinetic theory. Then we discussed the pressure excited by gas. We got this formula: pressure is equal to 1 by 3 N by V mv square average. By using mass density, we rewritten this formula like 1 by 3 rho V square average. Then we discussed the relation between pressure and translational kinetic energy, that is P equal to 2 by 3 E by V or PV equal to 2 by 3 E. From this formula, by using ideal gas equation PV equal to nRT, we derived equation for translational kinetic energy, that is E equal to 3 by 2 nRT or E equal to 3 by 2 NKBT. So with this I am ending my lecture. So very thanks for attending this lecture, and thanks. If you are new here, please subscribe my channel. Please subscribe and share it. Okay, thank you.